All right, let's dive right into this explainer and uncover the invisible architecture of our reality. I mean, think about it. Absolutely everything you can touch, see, or feel is built by a hidden world of tiny, constantly moving structures. Today, we're exploring the fundamental particle nature of matter. And trust me, once you start seeing the world this way, you can literally never unsee it.
We've got a fantastic roadmap ahead for this explainer. 1. The invisible particle world. 2. Solids, liquids, and gases. 3. The power of heat. 4. Changing states of matter. And finally, 5. The ultimate particle quiz to test what you've picked up.
Okay, Section 1. The invisible particle world, the secret mechanism behind reality.
So, have you ever wondered about these everyday mysteries? Like, how does a puddle of water just seem to vanish into thin air on a hot afternoon? Or how, if someone sprays perfume near the classroom door, people all the way at the back of the room can smell it just a few minutes later? Well, the answer lies in what matter is actually made of.
And that brings us to the kinetic molecular theory. Now, even though something like a wooden desk or a glass of water looks completely solid and hold to us, it's actually made up of tiny, microscopic particles. And here's the real secret. They are always moving. They've got little spaces between them, and they're constantly attracting one another. This theory is literally the master key to unlocking exactly how solids, liquids, and gases behave. Which leads us perfectly into Section 2. Solids, liquids, and gases, meeting the states.
What's really fascinating here is how these particles act kind of like crowds of people in entirely different social settings. For solids, you can see the particles are tightly packed in this super orderly pattern. They don't really move from place to place, they just vibrate right there in a fixed position. And that is exactly what gives solids a definite shape and volume. Now, for liquids, the particles are still close together, but those attractive forces are just a bit weaker, so they can slide past one another. That's why liquids flow and take the shape of whatever container you pour them into. And finally, for gases, the particles are way far apart. The attractive forces are incredibly weak, so they move freely and super fast in all directions, with absolutely no definite shape or volume.
To really contrast this, just think of a solid rock sitting on your table versus an invisible gas, like LPG leaking into a kitchen. The rock keeps its exact shape, right? That's because its particles are locked in this strong, vibrating embrace. The gas, on the other hand, has particles that are completely spaced out and weakly attracted, which allows it to rapidly spread and fill the entire volume of the room.
Let's ground this in reality by looking at a few everyday examples. Notice how the ice in your glass, the water you drink, and the steam pouring out of a kettle all look totally different at the microscopic level. Mind you, it is the exact same substance, water, but the arrangement, the spacing, and the motion of its invisible particles are entirely dictated by its current state.
All right, moving on to Section 3, the power of heat, the catalyst for change.
So, if particles are constantly moving, what actually determines how fast they go? Well, temperature acts as the volume dial for our particle dance floor. If you remember just one thing from this explainer, make it this golden rule. Adding heat increases the energy of the particles. When they get that energy, they move way faster and spread farther apart. And conversely, when you remove heat, cool something down, the particles lose energy, they slow down, and those attractive forces pull them right back closer together.
And that shift in energy, it isn't just a minor tweak. It's exactly what causes matter to completely transform. Section 4. Changing states of matter. As we systematically add heat from a source, maybe the hot afternoon sun or a stove, we actually watch the physical structure break down. First, a solid melts. The particles gain energy and vibrate so intensely they just break away from their fixed, rigid positions. Add even more heat, and the liquid evaporates. The particles are moving so incredibly fast now that they escape the liquid entirely and become a free-flowing gas in the air. And this illustrates the complete cycle perfectly. Following the heating process, you go from melting right into evaporation. But we can also throw it in reverse by removing heat. Gas condenses back into liquid, and liquid freezes back into solid. What's absolutely mind-blowing, though, is that you can even skip the liquid phase entirely. Take a look at sublimation. That's where a solid, like one of those dry air fresheners, turns directly into gas. Or deposition, where water vapor and freezing air turns directly into solid frost on the grass. Crazy, right?
This chart is a fantastic summary of these dynamic processes. It proves that whether you're leaving ice candy out under the scorching sun, popping some mango juice into the freezer, or just watching water droplets mysteriously appear on a cold glass, it all boils down to one simple, incredible mechanic:
heat being added to or removed from those invisible particles.
Okay, now that we understand the rules, let's see how much you've picked up. Section 5. The Ultimate Particle Quiz.
Let's start with a kitchen classic. Scenario 1. Imagine Nana is boiling water for coffee. As the liquid water gets hotter and turns into bubbling steam, what is the heat actually doing to the microscopic water particles inside? Here are your options. A. Are they completely destroyed by the extreme heat? B. Do they gain energy, move faster, and spread farther apart? C. Do they become heavy and sink? Or D. Do they just freeze up and stop moving because of the heat? Take a quick second to think about our golden rule of temperature.
Okay, if you guessed B, you hit the nail on the head. The particles are definitely not destroyed. Instead, the added heat gives the liquid water particles this massive injection of energy. They move faster and spread farther apart, eventually overcoming those attractive forces to escape right into the air as steam.
All right, Scenario 2. Let's look at a pretty critical safety situation present in so many homes. A family uses an LPG tank for cooking. A small gas leak spreads around the kitchen, even though the gas cannot be seen by the naked eye. Why is this specific phase of matter so dangerous in this situation?
Let's review the options. A. Gas particles stay only near the tank. B. Gas particles move freely and can spread quickly in a room. C. Gas particles are tightly packed and cannot move. Or D. Gas particles instantly turn into a solid upon leaking. Think back to the social behavior of gases we talked about earlier.
And the correct answer is B. Because gas particles have really weak attractive forces, they aren't held together like a solid or liquid. They move freely in all directions. So leaked gas will rapidly spread and fill the entire available space of the kitchen. It creates a massive fire hazard everywhere, even if you can't see the leak yourself. Okay, Scenario 3. For our final question, let's solve a classic hot weather mystery, the sweating glass. A freezing cold glass of calamansi juice is placed on a table. After a few minutes, liquid water droplets form all over the outside of the glass. What is the best explanation for where that water came from? Are your choices A. Water from inside the glass actually leaked out through microscopic holes? B. The glass magically created brand new water particles? C. Water vapor in the air cooled and condensed into liquid? Or D. The juice sublimated directly into gas? What do you think?
The answer is C. The invisible water vapor gas floating in the warm air actually loses energy when it hits the freezing cold side of your glass. That cooling causes those gas particles to slow down, come closer together, and condense back into liquid droplets right there on the surface. It's literally an invisible phase change made completely visible. Which leaves us with this final thought for the explainer. If absolutely everything around us is built by these tiny, constantly moving particles, what other invisible transformations are happening right in front of you at this very moment? Keep your eyes open and stay curious.